Hi guys. It was mentioned in class that some would like to see a review of the quadratic formula, so here's a quickie for you. Of course, the formula says that for any quadratic equation, a second degree equation in one variable, if you put it in standard form, ax squared plus bx plus c equals 0, then the solutions are x equals the opposite of b plus or minus square root of the quantity b squared minus 4ac divided by twice the leading coefficient, 2 times a. Let's look at an example, solving 3x squared equals 4x plus 1. Once we recognize that it's quadratic because of the second degree term on x, then we want to put it in standard form, and remind the car, by subtracting 4x and 1 from both sides to get 3x squared minus 4x minus 1, and then I can see what the a and b and c are in the quadratic formula. Now, a very nice approach to this before actually plugging into the full formula is to calculate the discriminant, the b squared minus 4ac, which is the radicand in the quadratic formula. Here, b squared minus 4ac is the square of negative 4 minus 4 times 3 times negative 1 equals 28. And what the discriminant tells me is the nature of the solutions for the quadratic equation. If the discriminant's negative, I get two complex solutions because I have a square root of a negative number, not real solutions, but solutions that would have I in them. If b squared minus 4ac is equal to 0, then the radical disappears and I'm left with one solution, opposite of b over 2a. But if b squared minus 4ac is positive, as in this case I have the discriminant equals 28, then I get two real solutions because of this plus minus a square root of a positive number gives me plus minus a real number in there. Now, often not mentioned in textbooks, if b squared minus 4ac turns out to be a perfect square, then the radical simplifies very nicely, and I would have been able to factor the equation. So a nice thing to do to determine whether you can solve this by factoring is to see if b squared minus 4ac is a perfect square. I'm not quite that lucky in this case, so let's continue with the full formula. So my solutions are going to be the opposite of b plus or minus square root of the discriminant. And cleaning that up a little bit, I get positive 4 plus or minus radical 28 over 6. Now, a very common error is to try to cancel common factors between these two numbers, which is not okay unless I also have a value over here that has a common divisor with these two. So I always want to start by simplifying the radical as much as possible. And looking at square root of 28, I see that 28 does have a perfect square divisor. I can break it down into radical 4 times radical 7. And I want to do that because this square root of a perfect square allows me to break this down and make that into 2 radical 7. So let's see, this becomes 4 plus or minus 2 times square root of 7 divided by 6. And now the fact that I've got a common divisor of 2 in 3 locations, 4, 2, and 6, all have a factor of 2, means I can simplify a little further. A lot of people will just cancel these 3 and divide each of the 3 by 2, which is fine. Technically what you're doing is factoring a 2 out of the numerator and then canceling a factor of 2 above and below the fraction bar. So what we've got here is cancel that 2 or take a factor of 2 out of here and here, and I wind up with 2 plus or minus the square root of 7 divided by 3. That's as nice as I can write these solutions if I'm giving exact solutions. If I'm asked to approximate them, say approximate to the nearest hundredth, then I'm going to use that approximately equal sign, and I'm going to run these on my calculator and get about 1.55 and negative 0.22 for solutions, approximate solutions to the quadratic.